Hi again, intermediate algebra students. It's time for another thrilling lesson online. Today is lesson 3.3, multi-step equations. Now, you recall, of course, when we studied about the order of operations, this PEMDAS looks fairly familiar. And of course, you remember the mnemonic that helps you remember that. Please excuse my dear Aunt Sally. And of course, that reminds you to do parentheses, exponents, then multiplication, division, addition, and subtraction. Now, the thing about the PEMDAS mnemonic device is we definitely want to go in that order when we are simplifying things. So we did last chapter when we simplified expressions, we go in this direction. That's what we're most familiar with. However, when we get now to chapter 3 and we talk about solving equations, this order of operations memory device is important because now we're going to go in reverse order. So I'm essentially going in opposite directions when I'm solving equations. And the reason for that is when we solve equations, we're trying to strip away any numbers or other variables that are added or cluttering up our variable that we want to solve for. So that's why we're going to do the PEMDAS in reverse. So that's what this lesson is all about, trying to solve equations through more than just one step. Alright, so we're going to go on to the next slide here and see what we have. Some examples here. Here's a good multi-step equation. You see this one has some multiplication involved, 2 times q. It has some addition involved as well. So what we'd like to do, remember, eventually we want to get to the point where our final answer is q equals something. So we need to undo things around the q. Now, according to the order of operations, that would say that we have to do any multiplying or dividing before we do adding or subtracting. But once again, because we're reversing this, we want to undo or strip away everything around this variable here. My first step then is going to be to do something with that 11. So because it's a positive 11, I'm going to subtract 11 from each side like that. Since I'm trying to get that variable by itself or strip away anything else close to it, I'm going to do the inverse or the opposite of that operation. So that leaves me with a 2q here equaling 3 minus 11, a little tricky, but I think you can figure out that that's negative 8. Now we have just a fairly easy one-step equation right here, and you know that I would now divide both sides by 2, and sure enough, this will give me my answer. Negative 8 divided by 2 is negative 4. So notice we did the addition first, then we did the division. See what we have? So this is a little bit trickier looking one. Again, another multi-step one. Sometimes students are confused here because of this minus sign in front of the variable. So we'll see if we can get that straight. Now, I want to solve for a. Again, I have some division here with that fraction bar. But my first step here is actually going to be to try to get rid of this 3. And since that's a positive 3, I'm actually going to subtract 3 from each side. That'll be my first step. What I have left then is still that negative a over 7. And a key thing, remember that negative sign is still there. And that's going to equal negative 2 minus 3. Again, think of it as negative 2 plus a negative 3, which is negative 5. Now, how am I going to get rid of that 7 there? Well, because I am dividing by 7 here, the way to get rid of it is to multiply. And because of that negative sign, I'm going to actually multiply both sides by negative 7. Because that should give me a positive value for a on the left side. That's what I want. So what this leaves me with here after I do that, these 7s will now cancel out on this side. Negative times a negative is a positive, so I should just have a by itself on that side. That's what I want. Meanwhile, negative 5 times negative 7 is positive 35. Remember, the nice thing about equations is that you can check them. And so I could quickly put 35 back in here. 35 divided by 7 is 5. 3 minus 5 is negative 2, so that works out. kind of tricky one that always baffles students a little bit. So it sure looks like this is a fractiony type 1 here. And as we've just been saying, it looks like we should do the adding or subtracting first. But you also may recall we talked about something called implied parentheses here. And so even though I don't see any parentheses, you should really note that there are some around that k plus 9. That keeps that numerator sacred in a sense. And what that implies is that I also want to do what's in there last. So really when I'm solving this now, my first step will be to do something with that 12. Since I'm dividing by 12, I'm going to multiply by 12 on each side. So by doing that, the 12s cancel out. And so I have left then just k plus 9 in my numerator. Meanwhile, negative 2 times 12 is negative 24. Like that. And now it's a pretty basic equation. To get k by itself, I'm going to subtract 9 from each side like that. And my final answer then becomes negative 24 minus 9, which is negative 33. These are tricky problems, so you want to pay close attention to those for sure. Kind of special problem that we run into in this lesson are these consecutive integer problems. And so they are a little bit tricky because we need to try to solve these. A lot of times you can solve them by guessing and checking, but the most efficient way and the way you're going to be able to get it all the time is by doing some algebra. Now, consecutive integers, consecutive means one right after the other. So when we write consecutive integers, we're thinking about n, and the number that comes right after it is just one bigger, n plus 1, and then the next one would be one bigger than that, n plus 2, and so on and so forth. And examples of that would be 7, 8, 9, negative 3, negative 4, negative 5, that type of thing. All right. Now, it gets a little bit trickier when we talk about consecutive evens and consecutive odds. Of course, consecutive even integers would be numbers like 2, 4, 6, 8. So they don't come right after one another. They are 2 apart. So if my first even integer is k, my next one will be k plus 2, 2 bigger. And my next one would be k plus 4, and so on and so forth like that, because they are even. Now, here's another mistake that a lot of people make. They automatically think that consecutive odd integers then should be k, k plus 1, k plus 3, because 1 and 3 are odd numbers. But in reality, they should be values like this. If you think about it, odd numbers, again, are 2 apart all the time. So, once again, they would be very similar, in fact, identical to the consecutive evens. And we would write them like this. W, W plus 2, W plus 4. Now, let's actually look at a problem like this and see if we can solve it. Alright, so find 3 consecutive odd integers with a sum of negative 51. You might be able to guess and check at this fairly well, but again, the algebra will make it more efficient. So my first integer is going to be n. My next one, remember, will be 2 bigger, so it has to be n plus 2. My next one will be 2 bigger than that, or n plus 4, and it's going to equal negative 51. Now, you can simplify these. Notice that you have a single n on all these, so I can put the n's together. So I end up with 3n. And I also look at the numbers here. I have 6 when I add those up. So this turns into the equation 3n plus 6 equals negative 51. Typical multi-step one. My next step would be to subtract 6 from each side like this. So I'll get that 3n equals negative 51 minus 6 is negative 57. To solve this, then I'll divide by 3. This does work out pretty well. So n ends up to be negative 19. And as far as my consecutive integers, and I just keep adding 2 to each of these, so my next integers then would be negative 17 and negative 15. Those are my 3 consecutive odd integers that add up to negative 51. All right, thanks for listening, everybody, and we'll see you in class tomorrow. Bye now.